The Intercollegiate
Psychedelics Network.
Hi everyone, my name is Rumstein. I just finished my sophomore year at Columbia where I study cognitive science, and today I'm going to be talking to you about psychedelics and artificial neural networks and artificial intelligence, why, how, and what we have to gain from this field of study. And so I'll start with the question of what do artificial intelligence and psychedelics have in common? And being that we are here today at PsychedelX, I'm assuming that many of you probably know the answer, which is that we don't fully understand the potential of both of these fields. So today we're going to be talking about the intersection of both of them and what we have to gain from researching that intersection. So clearly, artificial intelligence and psychedelics are fields of study that are already being explored in tandem by different universities, including McGill and MIT. And they're using AI to analyze different substances, make sure that they're safe for people. They're also using language models to analyze trip reports, to look at the replicability of certain experiences, and just to help us understand more about the psychedelic experience in general. So clearly, this is something that is already being researched. Today, we're going to be talking about a different application of this, and it's that we're looking at the simulation of the substances in artificial neural networks. So the question is why? Why would we simulate psychedelics in artificial neural networks? Well, one, on the research and exploration front, we would learn lots more about the molecular mechanisms of the brain and psychedelic uptake. We would learn more about neural network effects and feature visualization, which is a component of the effects. We would also get to learn a lot more about consciousness studies. If we can create a biologically plausible model, we would learn more about sort of the top-down versus bottom-up effects of psychedelics. So how much of the experience are we generating in our own heads and projecting out into the world around us? How much of it is sort of like empirically available and then experienced through us in that state? So we get to learn lots more about that. On the therapies and harm reduction front, stimulating these experiences for people with sensitive neurochemistry or people who are taking psychotropics and don't really want to mess with that too much. We'd be able to give these people these life-changing visionary experiences without putting them at risk or causing anyone any harm. So if we could be able to replicate that, it could be amazing for people. We could investigate optimal dosing and environments, obviously without putting anyone at risk, by putting different models through these experiences and playing with the maybe perceived environment or the dosing. We could learn more about how to potentially administer an optimal psychedelic experience for a participant. And then AI for training purposes, basically like letting practitioners of psychedelic assisted psychotherapy take an artificial intelligence model through psychedelic experience, engaging with it on a language level, but also like conditioning sort of the practitioner for like how to feel and how to show up in that space in order to create the best kind of experience that they can for the participant. Could be really, really great. And understanding individual variability. So testing on a variety of different models that are biologically plausible, and learning about what different kinds of models need essentially in order to have a good trip. And then also just broadly advancements in AI. Dudeveloping biologically plausible brain models would allow us to learn more about short-term synaptic modulation, which is essentially what is happening during the psychedelic experience. And then also the output, essentially, for inputting psychedelics in artificial models is a mystery. What we have here for you in this model on the bottom right is what happened when I input simulating DMT in artificial neural networks, and this model called Midjourney, this image processing model, put out these amazing images. The one on the bottom right kind of looks like an EEG cap, and the one on the left like have these like sort of like neurospindly kinds of shapes, which to me means that the model recognizes that we're talking here about neuroscience, we're talking about psychedelics, we're talking about the brain. and the systems within the brain. And so to put it into an image processing model and to get these images, or to put it potentially through a language processing model, would help us learn about how much of this stuff is empirical, how much of this iconography is sort of like available across the board, and how much of it is specific to humans, how humanly specific is the psychedelic experience. So I think that's a really interesting field of exploration. So the title of this talk was a little bit more broad. It was talking about stimulating psychedelics. Clearly, I've chosen to go with DMT in the specific talk. So the question is why? Why DMT? So DMT is a highly visual model, which would be able to basically give us the most to interface with when we talk about the kind of ANN, which is a CNN, convolutional neural network, which is trained to specifically work with images. So working with a highly visual psychedelic like DMT would allow us to interface with the most information and to compare essentially the most between biological models and artificial models. And also, we have lots of information about DMT, especially after the Controlled Substances Act of 1971, and Rick Strassman decided to reawaken that research in the 90s, taking very, very detailed chip reports that would give us really solid information to compare essentially the experiences between what we're able to replicate in artificial models and what we know about the human experience, the biological experience of DMT. So that's why I chose to talk about DMT today. All right, so we're talking more broadly about the biological neural networks that exist in our brains and how we can use their design to inspire the artificial neural networks that would be most biologically plausible. Most specifically the CNNs, the convolutional neural networks that deal with image processing, like I mentioned earlier. All right, so let's look at biological neural networks versus artificial neural networks. So BNNs are complicated models of natural machinery, whereas artificial neural networks are more simplistic and they are reduced models of the same behavior. Artificial neural networks have mathematical descriptions, whereas biological neural networks are in vivo. Artificial neural networks use weight tuning to create outputs. Biological models do not have that functionality. So we look here in this model over to the left. So the model on the left is looking at an artificial neural network. The input gets aggregated in the soma, and the action potential will either reach the voltage threshold required for the activation or not. So that is something that is unique to the artificial neural network, whereas the biological neural network will rely on action potentials to create outputs. So let's talk a little bit more about biological neural networks. So what are they? They're biological models. Scientists model artificial neural networks based on the structure and function of BNNs because we know that they work well. The advantages is that they can learn and react to new stimuli in ways that artificial neural networks cannot. Obviously, after biological neural networks have gone through billions of years of evolutionary pressure to in the best way, artificial neural networks can't even begin to touch that level of optimization. The limitations of working with biological neural networks is that creating the biologically plausible models of them is really complex and expensive compared to the more simplified models of neural networks, which are relatively cheap and easy to create, which is why we have a proliferation of them on the internet these days, especially 2023 being like the most active year for open access artificial intelligence. And then the future applications of biological neural networks would allow us to better implement ANNs, and it would enable us to create more complex and sophisticated simulations, which is what we spoke about a little earlier, and we'll talk a little bit more at the end, what these simulations, what we can gain by creating these simulations. All right, so now let's talk about artificial neural networks. What are they? Type of computational model designed for decision making and prediction. So we have an input, there are hidden layers in between, and then as the input passes through the layers, it creates an output. It can predict the output that we're looking for to reflect the input. The advantages of working with them is that they're well suited for processing and analyzing visual data sets like text or audio. And in comparison with convolutional neural networks, which are technically a kind of artificial neural network that are specifically designed to work with images, is that they are better for decision. The ANNs are better for decision making than CNNs. CNNs are better for visual identification and recognition. So if we talk about if we're looking to replicate sort of like the motor and language effect of a psychedelic, we'd probably turn to the broader artificial neural networks, whereas the convolutional neural networks are best applied for visual inputs, like what we were talking about earlier with the DMT visuals. All right, so why are artificial neural networks implausible? So we can currently produce the trippy psychedelic visuals using the CNNs, but we don't have anything that is biologically plausible that can produce the same effect, right? So we spoke about Midjourney earlier. I put in the prompt. It created these like wonderfully trippy visuals that look very much like someone might expect to see on a DMT experience, but they were not creating the same qualitative effects as a biological model is experiencing during DMT uptake. The ANNs are really cool because they operate using something called weight sharing, so we can manipulate these weights or a series of abstractions that are able to take the same principles of the way that signals are computed in BNNs without limitation. So we can do all kinds of interesting things to sort of change the input, and that will affect the output. So that's not something that we don't have that level of granularity with biological neural networks, but it is something that we do have with artificial neural networks. We have like the BNN being like the actual car, the one that you can drive, the one that gets you from point A to point B, the ANN being what looks like a car but is not qualitatively the same. All right, so now we're moving towards a model that is closer to a biologically plausible one, but is not quite. So we have the SPA model or the BioSPA model, and basically it uses a large-scale brain model that includes 31,000 compartmental neurons and 37 million synapses to essentially mimic the way that a brain works. It's not quite as complex or as far ahead as an actual biologically plausible model, but it was called like the largest brain model that we had to date. So that's something. And the challenge here is that the model uses what they call simple, leaky, integrate, and fire, which aren't as complex or sort of adept at processing information as actual neurons, but gets pretty close. So why are we talking about biospan? Well, it was used to simulate the effects of tetrodotoxin in both the visual and frontal cortex, which is really interesting because what we're talking about here is the potential to simulate psychedelics in a model. So if we know that we can already use a toxin like tetrodotoxin to affect the behavior of the model, essentially disinhibiting it or sort of making the outputs kind of wonky when we give it a task, we know that it's possible to change the weights within an artificial network to sort of mimic the effects that we get with a psychedelic. So here I will show you a video of what happens in the biospan model when it's given a task. Essentially, it's shown a picture. It's shown a bunch of inputs, sort of series of inputs, and then it's eventually asked to replicate the output of an input that it's never seen before. So 0 is the new input that it's seeing, and then we can see here that it is able to create that relationship. Eventually, it does find a 0. It's able to create the accurate output, the one that's expected of it. And then, so later, researchers at the same lab that work with this model did the research with the tetrodotoxin and found that they were able to manipulate the results of a task using the stimulation of the neurotoxin. All right, so now let's talk about convolutional neural networks. So what are they? They're a type of neural network designed to analyze visual inputs, which is why we're talking about DMT today, which is a highly visual drug. The advantages of working with it is that it can identify complex patterns like faces and are widely used in image recognition. The problem is that they're not as effective at analyzing non-visual data or making decisions based on data. So obviously we're not talking about the broader qualitative effect of the psychedelic, but it's really good at telling us about the visual components. So the way that it learns features, how does it do this? It's kind of like a puzzle-solving brain. It uses filters to find patterns, create feature maps, and pooling to focus on the important parts. So we'll talk a little bit more about that now. So how are they able to produce consistent details at both high and low levels? And essentially, their different neurons are trained to prefer or to detect certain kinds of figures. We have edges, textures, patterns, parts of objects, varying in levels of complexity, but the neurons are trained to look for these shapes and then to replicate them. So there are different optimization objectives that show what the different parts of the networks are looking for, right? So we have a neuron that's looking for a certain kind of pattern passing through that layer that we spoke about earlier. And as it passes through the layer, it becomes more and more complex until we have something that looks really, really complex, something like that. And that's how it's able to replicate the consistency from low levels of complexity to high levels of complexity. All right, so now as we get towards the end of the talk, let's compare and contrast the three concepts of the networks that we spoke about today. So we have the convolutional neural networks that would be researched mostly by artificial intelligence and computer scientists, people who are interested in those fields. They'd be designed for visual tasks, which are kind of algorithmic tasks, but are a little bit more specific than that. So they'd be recognizing patterns in visual data sets, but unfortunately they'd be less effective on non-visual data. So using that aspect of the CNNs to look at the visual data to help us replicate the visual experience of the journey, but not very much beyond that. We need another model to sort of help us create that more holistic and complex experience of the simulation. But the way that it'd be used is to model the visual pathways that are active during psychedelics. So modeling that visual pathway that leads to that allows us to see the sort of trippy, awe-inspiring visuals that we're used to in that space. Talking more broadly about artificial neural networks, they'd be researched by computer scientists and computational biologists, and they're designed for algorithmic tasks. Language and motor outputs would be examples of that, which would, be the sort of the missing pieces that the CNNs don't have. Would be the missing pieces of the simulation that would sort of combine with the visual components to create that robust experience. They process and analyze non-visual data, like we spoke about earlier. They are computationally constrained, but they would help us model functional changes during psychedelics. So what are the functional changes, the qualitative changes that are happening in consciousness during those experiences? And then the biological neural networks, as we continue to build more biologically plausible versions of them, they'd be explored by computational biologists, sort of like drawing this thread of complexity and then moving more towards people who are in the natural sciences, like neuroscientists, to explore these models that are right now, they're evolutionarily designed for life. They're what keep us alive. They're what allow us to experience a psychedelic state, and moving towards models that work most like that. They learn and they react to new stimuli, which is novel and something that people can argue is uniquely human. The limitations of these models is that they're really complex and expensive to create and study in the real world. Also, it's kind of invasive. Like as we want to learn more about the neuromechanisms that or the neuroscience that's happening, as we want to learn more about that, we need to do more and more invasive research into the brain in order to learn and then simulate those processes. So that's difficult and expensive and dangerous, but it would allow us to explore more empirical validation of psychedelic studies and biomimicry, which is really, really valuable as we try to create these models that would allow us to expand our therapeutic possibilities and increase safety in our research around psychedelics and the psychedelic experience. All right, so our conclusion, what are we looking forward to? So as technology and research continues to advance, neural networks continue to unlock new insights into how the brain functions. So, psychedelics is one way that we could apply this, but we could also apply it to neuroscience in general and just learn more about consciousness, stuff that we may not have access to just based on the way that we conduct research ethically. And we'd have new research tools. Their neural networks have a wide range of interdisciplinary research opportunities, right? So we talked earlier about creating those sort of like therapeutic simulations that would allow us to learn about the way that psychedelics affect us, but we could also learn how other drugs affect us. And then the future potential, more research into neural networks of all kinds will contribute to a more holistic and comprehensive understanding of psychedelics. So we have the harm reduction front, the therapeutic front, but also just knowing how to sort of elicit those responses in the brain without changing neurochemistry is a really interesting and impactful front for lots of folks. And then also just like playing with AI. It's really interesting when I have these graphics that were produced by Midjourney, just by giving it a simple prompt like that. Imagine putting it through, putting ChatGPT through a DMT experience and seeing sort of what it spits back out at us, teaching us about, what's sort of like in the collective unconscious about psychedelics and the psychedelic experience, what's deeply personal and what's actually available to systems beyond us, like artificial intelligence, and what does that tell us about the information that we're accessing in the psychedelic state. So thank you guys so much for listening. I hope that you're inspired to ask questions about artificial intelligence, to hopefully invest in this research. And thank you guys so much for listening. Have a great day.